Welcome to the audience. I'm Heiko, and I want to show you in today's topic how industrial cameras have evolved in the past years and how they are still differentiated despite of their standardization. So let's start at our journey at the very beginning. What you see here is really a nice piece of camera, but I think we don't have to go back quite that far. That would also exceed the time frame a bit. So let's jump directly to the time of the analog cameras. It was not so long ago that camera image data was an analog television signal transmitted via a coax line, which first had to be digitized for the image processing in the host PC. Frame grabber plug-in cards with digital to analog converters were used for this purpose. The data flow in this case was rather a one-way street, so communication or configuration of the camera itself was hardly possible or only at limited level. However, even at that time, the system architecture of the whole machine vision software system already consists of the most fundamental components. We have the camera, we have a data transfer to the host PC, we have a low-level software for managing the hardware. We have a software development kit with a programming API. And last but not least, the individual custom application where the data was processed. The position of the cogwheels show that most of the video signal pre-processing and handling is done in the PC software. When we jump to the time from the digital cameras, it was possible for the first time to implement a complete data path in digital form, from the image sensor to the image processing in the host PC. In addition, since then, the sensors can be controlled and configured via a communication channel through the PC application. Cameras with interfaces such as Firewire, USB, and Ethernet were developed for send and receive digital data and commands without a need for additional signal converters. Depending on the performance level of the cameras, also high-speed interfaces such as Camera Link were introduced. In conjunction with ever larger, faster, and higher quality sensors, manufacturers have been able to continuously increase the data quality for image processing during this time. However, the number of interfaces has also increased, which made it somewhat intransparent for the user choosing the right hardware-software combination. That's why, with the machine vision standards, the industry has agreed to work together in an unequaled way. This collaboration with the AEI and EMVA organization represents an important step in bringing the interface confusion in the machine vision environment under control again. The design-in process of cameras in applications should again be simplified and shortened and additionally save development costs. Interchangeability and complete plug-and-play of cameras were also always essential requirements. Even in this standardized machine vision system, of course, the system architecture remains the same with the basic components we know already. However, with GenICam as a basis, standardization took place at several interfaces in this system structure. The hardware still uses the connection technologies for transmitting camera data, such as USB or the gigabit Ethernet network. But with USB 3 vision and GigE vision, they are based on uniform protocols. And also a standardized device-related software now operates between camera and the user application with a uniform API. On the one hand, this ensures a universal language with application software. On the other hand, it eliminates the strict relationship between camera firmware, transmission protocol, and device software. This means that the camera hardware now works independently of any special manufacturer software. With the standard feature naming convention, the scope of functions, function names, and the behavior of the camera have also been defined and standardized. In addition to a mandatory range of functions, there are also other important, the recommended and optional functions. The resulting generic interface for cameras, so-called GenICam, thus describes and abstracts access to all available camera features across manufacturers and transport protocols. This makes GenICam the perfect application basis when features change with each camera model or can be extended by firmware updates. And very important is also, this interface works for all standard cameras equally. So it does not have to be from the same company as the camera. Many of the well-known image processing frameworks are nowadays vision compliant and provide their own generic camera interface, making the integration and use of vision cameras fast and uncomplicated. So the user can work with his own transport layer or let the existing vision connectors integrate his camera. Software manufacturers, such as MVTech, are thus taking full advantage of the standardization. With Helcam, the user can therefore start image processing directly and even without any programming effort for camera integration. The user only comes into contact with the standards via a dynamic and graphical interface, which makes it very easy for the user to deal with it. You can read more info and background about GenICam, the camera compatibility and independence in our white paper on our website. It's called interchangeability or compatibility. So, however, the camera standardization also demanded important changes for the manufacturers. If cameras have to operate independently of a specific manufacturer software, they must themselves ensure that they generate usable output data. This means that functionalities for processing the raw sensor data must migrate into the camera. This includes functions such as debayering, gray level transformation, defect pixel removal, or white balance corrections. To run these pixel operations with high performance in the cameras, so-called pixel pipeline or image pipeline, specific hardware components like FPGAs are required. But these kinds of improvements have the side effect of increasing camera costs, energy consumption, and thus heat generation. But what does that mean for the customer? With all these changes through the standardization, will cameras now be much easier to select? If the selection does not reduce to core ingredients such the image sensor, the interface, the range of functions, and the price? We must say yes, the standardization has created additional opportunities to compare camera features. But the selection or suitability of a camera for a particular application cannot be made simply on the comparison of the pure values of these characteristics. Let's look at another example of this. Buying something from Amazon. We all know that. We look for a product we would like to have. When we find something, we start comparing. And Amazon apparently makes it easy for us and lists our product compared to other similar products in a comparison list, like you see it here. Some are cheaper, some are more expensive. If we are lucky, we actually find a difference in this comparison list. But for the most part, the products look very similar. And what comes next? Do we just buy the cheapest one or the one with the most features in the same price range? In this case, the green cordless screwdriver, obviously it offers the best price performance ratio of all when you look at these values here. Of course not. We start to compare. We read in product descriptions, reviews, and watch out. The supposedly cheaper product with the most features is a disaster. Gets hot, defective after 3 days, poor support, no return option. The list is long. But come back to the cameras. So we see that also other features are not less important when comparing cameras, like the form factor of a camera. For example, the size itself can be crucial for the integration into an application. Or which mounting options are available and do they remain equal with each hardware revision? Especially for machine vision builders, these criteria can be crucial as changes always cost time and money. And is smaller always better? Especially high performance functions generate a lot of heat that has to be dissipated. In rough environments, high protection glasses are also important. And in some cases, you may need the camera without an housing. How flexible are the manufacturers in this? Furthermore, the quality of function implementation can also be very different, even when the function names are equal. For example, triggering of the image acquisition is one of the most important functions of an industrial camera. But how many ways of triggering are there? Cyclic, delayed, triggered exposure time, counted image sequence with fixed frame rate, and how can you control them? Is the desired image always captured safely? Or is there a jitter in the delay time? So you see functions from different manufacturers, and thus the cameras are never the same. So before evaluating a camera's feature, it is essential to first check the requirements of the application. Only these give weight to the camera features. So think about what the camera is actually supposed to do, who will work with it, in which environment will it be used, or whether you might need a special customization. Take, for example, an application from the medical field, like this here. For a high throughput bioanalysis workflow, simple but time-consuming individual tasks are to be automated using industrial cameras and state-of-the-art image processing. Each individual step requires several cameras that record image series in a narrow space at low frame rates and in only a 1 megapixel range. But this allows capturing characteristic features and changes of several samples in parallel to ensure a high throughput. Compared to the previously used laboratory microscopes, the amount of data can thus be significantly reduced. The laboratory environment itself provides ideal light conditions, which also means, for example, that no continuous automatic image adjustments are necessary. Accordingly, no special pre-processing is required in the camera. And standardized interfaces should simplify camera deployment and image processing. So you see, every machine vision application has its own challenges regarding the camera selection. Sometimes, like in our example, it is necessary that the camera is small in size and reduced to the basic essentials. In other examples, in other applications, high performance, full-featured cameras must take over the pre-processing in order to support the PC at very high data rates. Especially during design-in, it is also important to have a reliable and competent partner who can help you with the selection of the necessary hardware as well as possible customizations. To be able to support these requirements is our daily challenge at IDS. Therefore, we offer the complete range from the cost-sensitive standard camera up to the full-featured factory automation models within our UI+ portfolio. A very similar challenge we see on the software side. In the IDS Peak session, we will have a closer look to the requirements to a modern software development kit and how you get the best out of your camera hardware by choosing the right software. So thank you for listening and have a look into your session calendar. Bye.